Hello everyone, we are Team 3 Hyungjun Jo
and Nazia Praveen.
from the GIST. We are presenting our research proposal for the course Medical Engineering. Our project is called Re-Endothelialize, an endothelium limiting coating that could finally make long-term, small diameter artificial blood vessels possible. This isn't just a new coating, it's our attempt to solve a problem that has stayed open for 40 years.
Let's start with why this matters. Every 33 seconds, someone in the world dies of cardiovascular disease. About 18 million deaths a year. For many of these patients, the treatment is bypass surgery. In the US alone, 240 and 400,000 coronary bypass operations are done every year. But here's the problem. The vein most commonly used as the bypass fails in about half of patients within 10 years. So, bypass surgery saves lives, yet the graft itself is the weakest link. Why don't we just use an artificial vessel? For large vessels, we already do. Above 6 mm, like the aorta, synthetic drafts of Dacron or expandable polytetrafluoroethylene works very well with patency over 80% at 5 years, and they are available off the shelf. But the moment we drop below 6 millimeters into coronary, peripheral or pediatric vessels, everything breaks down. The flow is slower, so clots form. There is no endothelium, so the surface is thrombogenic, and the stiffness mismatch causes scarring. To this day, there is no FDA approved small diameter graft. The root cause is simple. The body reads every synthetic surface as a wound and tries to seal it. Here's the landscape of what we have today. The patient's own vessels work best. The memory artery is the gold standard at over 90% patency. But supply is limited and harvesting is invasive. Synthetic grafts are off the shelf but fail below 6 mm. Heparin coatings help but wash out in weeks. And tissue engineered grafts are promising but takes months to culture per patient. Every option fixes one part of the problem. None is both durable and ready off the shelf. So let's see what goes wrong in seconds. Let me show you how a synthetic graft fails. Within 1 second, plasma proteins coat the surface. Within 1 minute, platelets stick and activate. Within hours, the clotting cascade builds a fibrin mesh and a thrombus forms. And within weeks, smooth muscle cells overgrow the channel until it closes. There is exactly one surface in the body that resists all of this, the endothelium, the natural lining inside every healthy vessel. So instead of fighting the body, our strategy is to build a coating it recognizes as endothelium. Let's look at the significance where the need is greatest. In coronary surgery, up to 95% of bypass patients receive a vein graft and 40 to 50% of those fail within 10 years. But the pediatric case is even more urgent. About 40,000 children a year undergo congenital heart surgery in the US and around 3,000 in Korea. For them, today's conduits can't grow with the child. They degenerate and have to be replaced, meaning repeat open heart surgeries. A graft that integrates and grows would change those children's lives. It's the same core problem as adults, just with higher stakes. Let's look at our research goal. We are not the first to try. Over 40 years, researchers proposed many clever ideas, but each fixed only one piece. Heparin coatings prevent clotting, but deplete in weeks. Cell seeding builds a living lining, but takes months. Deuterinic polymers resist fouling, but give no healing signal. Tetrapeptides attract endothelial cells, but don't stop platelets. And nitric oxide coatings mimic the body's anti-clotting signal, but the donor runs out fast. So, our research goal is to stop choosing one and combine passive resistance, active antithrombotic signaling, and selective endothelialization into a single self-renewing coating.
Let's look at the heart of our proposal, our hypothesis, a coating that combines anti-fouling chemistry, catalytic generation, and endothelial selective adhesion will improve patency by reducing thrombosis while accelerating re-endothelialization. It's a three-layer living mask, and each layer recreates one job of the natural endothelium. Layer 1, the anti-fouling base, that mimics the cell membrane so blood proteins simply don't stick, blocking the very first step of failure. Layer 2, the catalytic anode generator, that is our key innovation. Instead of storing anode and running out, we immobilize copper ions that convert molecules already in the blood into anode on demand. Because the raw material comes from the blood itself, the coating keeps producing anode essentially indefinitely. Layer 3, the endothelial magnet, RDDV peptides that selectively bind endothelial cells but ignore smooth muscle cells, so the right cells move in and rebuild a healthy lining. Three layers, anti-fouling, anti-clotting, and pro-endothelial, and it renews itself rather than wearing out. Next is a 5-year plan. Here's how we execute over 5 years in 1 year run. Build a coating and verify its durability and annual release on EPTFE. Aim 2 years 1 to 2. Test it in human blood and cell cultures, targeting at least an 80% drop in platelet adhesion and a threefold preference for endothelial cells. Aim 3 years 2 to 4. Animal validation. With carotid first, then a porcine 4mm graft with a 6-month patency endpoint. And aim 4 years 4 to 5. Scale up and regulation, including a free IND meeting with the Korean MFDS and the FDA. Importantly, there's a go, no-go decision after aim 2. We only enter expensive animal studies if the selectivity target is met. Every honest proposal answers, what if it doesn't work? If anode depletes too fast, we switch to a fully catalytic copper system that consumes nothing. If the coating feels off under arterial pressure, we add a muscle-inspired polydopamine anchor test on the bench first. If our animal model doesn't predict humans, we run a vascular graft on a chip with human blood as a bridge. And if regulation drags, we engage the MFDS early. Risk management is built into the timeline, not bolted on at the end. Let's look at our future perspective and impact. If it works, who benefits? Patients first. No pain per vein harvest, a graft ready immediately, and for children, one that can grow with them. Clinicians get shorter operations, predictable graft quality, and fewer reoperations with the same workflow they already use. And the healthcare system saves on the roughly 13% of bypass patients who need repeat procedures within 10 years. The same platform extends to dialysis and assist devices. A vascular graft market around $3.7 billion, growing about 7% a year, with very export potential for Korea. Last is summary and conclusion. To summarize, the problem is that small vessels have no durable artificial option. Our idea is a three-layer endothelium mimicking coating. What's new is that the anode is regenerated from the blood, not stored and depleted. The first designed to combine all three functions in one surface. And the payoff, if we hit 80% patency in the porcine model, is a platform that reaches far beyond bypass surgery. I will leave you with one idea. The body reads every synthetic surface as a one. We are teaching it to read our coating as itself. Thank
Thank
you
you for
for listening.
listening.
We'd
We'll
be
be
glad
glad
to
to
hear
hear
your
your
questions
questions
or
or
ideas.
ideas.